Well, hello, I'm Mrs. Edwards, and today we're going to be rewriting quadratic equations in the form y equals ax squared plus bx plus c in vertex form, which is the y equals a times x minus h quantity squared plus k. To be able to do this, we're going to complete the square. Before we start completing the square, we're going to take a look at some trinomials that are perfect squares to look for some patterns. Then we'll be able to apply those patterns to complete the square. Here I have 4 trinomials and they are all perfect squares. So how do I know that they're perfect squares? Notice one of the patterns. The b term divided by 2 and squared is the c term. 8 divided by 2 is 4. 4 squared is 16. 10 divided by 2 is 5. 5 squared is 25. Negative 4 divided by 2 is negative 2. Negative 2 squared is 4. Negative 12 divided by 2 is negative 6. Negative 6 squared is 36. All right, so that's how we know they're perfect squares, and that is also how we can get this plus c. When we go to factor each one of these, and I'm just going to do that very quickly because we're just going to be looking for some patterns. How do I know that that's plus 4 or that's plus 5 or that's negative 2 or that's negative 6 without much thought at all? Well, notice that this number here is just the b term divided by 2. 8 divided by 2 is 4. 10 divided by 2 is 5. Negative 4 divided by 2 is negative 2. Negative 12 divided by 2 is negative 6. Let's see if we can take those observations and just create some perfect squares. We're going to build up to starting with a quadratic formula, a quadratic equation in ax squared plus bx plus c form and turning it into vertex form. Let's create a couple of quadratics that are perfect squares. Applying what we just observed, what would the c be? Well, we would want to take the 4 and divide that 4 by 2 and square it. So when you take 4 divided by 2, you get 2, and squaring it, you get 4. So putting a 4 there would make that a perfect square. Now, as you start moving down your paper, every line has to be equivalent to the line above it. So right now, I can't just randomly add plus 4 because now this line does not equal this line. So to keep this line equivalent to this line, we're just going to turn around and undo the plus 4. Notice if we were to simplify that second line, we would be right back to the original. This is now a perfect square. So if it's a perfect square, we can factor it. Now we could very quickly factor this into a perfect square if you remember that whatever this number right here is, if we divide it by 2, which we got 2, that is going to be the number that goes there. You could go ahead and factor it if you want, but that's just a shortcut that whatever that number was divided by 2 is going right there. And then we still have that minus 4 on the end. Okay, let's try to complete the square here. To complete the square, we observe that this number is 10. We're going to think of a number that we should put here that's going to make this a perfect square. So we take the b term, divide it by 2, and square it. 10 divided by 2 is 5. 5 squared is 25. So we have plus 25. But because this line has to equal this line, we don't have an equal sign. So what I do to one side, I can't do to the other because there's no other side of an equal sign. So we're going to turn around and just undo the add 25 with minus 25, and now this second line is equivalent to the first one. this piece right here is now a perfect square. The number that goes right in here, that is going to be 5. If you want, you can factor x squared plus 10x plus 25 and get x plus 5 times x plus 5 and rewrite it as x plus 5 squared. That's just a nice pattern to realize that this number divided by 2 goes right there. And we still have that minus 25 and we bring it down. Now we're going to take a look at a lot of examples of completing the square because there are several little subtleties within each problem. So I've tried to choose examples that would allow you to see every possible scenario. We're going to apply what we just observed to complete the square. So the first thing we want to do is check to make sure that the leading coefficient is 1. You cannot complete the square if the leading coefficient is not 1. All right, so notice up here, this is 1x squared. So now that the leading coefficient, we've verified it's 1, we can move on. We're going to take that 13 and slide it over to the side. We're sliding it over to the side because the 13 does not make this a perfect square. We need to think of a number that would make this a perfect square. So we take that negative 6 divided by 2 and square it. Negative 6 divided by 2 is negative 3. Negative 3 squared is 9. So the number that's going to make this a perfect square is positive 9. But every line has to be equivalent to the one above it. Currently, if I added 9 and then added 13, I would not be back to the original. So I need to turn around and subtract 9. If I simplify this line, I'd be right back to the original. The first part of this is a perfect square, so we're going to write it as a perfect square, and negative 9 plus 13 made 4. When you factor x squared minus 6x plus 9, you're going to get x minus 3 times x minus 3. A shortcut is just to realize the number here is always half of this one. So negative 6 divided by 2 was the negative 3. So negative 3 is going to go right there. The benefit of vertex form is the vertex stands out. So what is the vertex? It is going to be the opposite of the number in here. So it's going to be the x that makes inside the parentheses equal to 0. So that's 3, comma 4. Another way that you could write it instead of 3, comma 4 as the coordinate, you could also write that as f of 3 equals 4 as we start using function notation more often than we use just a coordinate written like this. But either one of these is just fine. Next, we can find the line of symmetry, that vertical line that's going to cut the parabola in half. And the equation for that, let me just go ahead and graph as we go. So I'm going to make a sketch. There's 3, 4, the vertex. Okay, my axis of symmetry is x equals whatever number is the x in the vertex, or whatever is the opposite of this number. Okay, but it's this guy here, and it's an equation. So please don't write just the number 3. The equation of a vertical line at 3 is x equals 3. So there's our line of symmetry. Next, the y-intercept. Well, back here in ax squared plus bx plus c form, the nice thing about this form is the c value is always your y-intercept. So our y-intercept is 13, but it is a coordinate. So I'm going to say that we have 0, comma 13. When I move right 0 up 13 and plot the point, I'm going to put that right about there. This is just indicating that another way to write the coordinate 0, comma 13 is to say f of 0 equals 13. The next thing I can determine is whether this parabola opens up or down. The number in front of x squared is a, or in this case here also, a is 1. When a is positive, the parabola is smiling, and when it is negative, it is frowning. So in this case, we have a positive number right here, or you can think of it down here. A is positive. So I'm going to sketch in my parabola because it opens up. Now, if you completely understood that last example, feel free to fast forward through until you get to the next example, because this one is really just a repeat to make sure you have it down. All right, so we check to make sure the leading coefficient is 1, and we do have positive 1. Next, we're going to scoot over that plus 14. We're clearing a space so that we can choose our own number that will make this a perfect square. When we go to choose the number, we take the 8 divided by 2 and square it. So we have 4 squared, which is 16. So now we have a perfect square. But we have to undo what we just did so that this line is equivalent to this line. What we've written in the front is now a perfect square. And the number that goes here is 8 divided by 2, which is 4. Not a coincidence that it was the number before you squared it. So we're going to put in our 4, and negative 16 plus 14 is negative 2. Now that we have vertex form, we can identify the vertex. So it's going to be the opposite, comma negative 2. So negative 4, comma negative 2. Making a sketch of this parabola, there's my vertex. Axis of symmetry is a vertical line, so x equals whatever this one is. So in this case, x equals negative 4. So there is that axis of symmetry. Okay, the y-intercept, we can find the y-intercept because the plus c there, that is our y-intercept. It's a coordinate, so I'm going to say 0, 14, right? 0 up 14, plotting that one. It's going to be way up there, almost off my graph. Okay, and then opens. There is a positive 1 in front of the parentheses. That's the A. So it's opening up, and I can sketch in my parabola. Here's another example. But notice this time, the leading coefficient is not 1. You can't complete the square until that leading coefficient is 1. So what you do next is you want to factor out the leading coefficient from the first two terms. So notice I slid over the 12 because I'm not going to do anything with that for a while. But I'm going to factor out the 3 from those first two terms. So 3 divided by 3, 1x squared. Negative 6 divided by 3 is negative 2. So I factored it out. Now inside parentheses, I have 1x squared minus 2x. So we do have a leading coefficient of 1. So we're going to complete the square in x squared minus 2x. So to complete the square, we're going to take the negative 2 and we're going to divide by 2 and square it. So if we divide by 2 and square it, we have negative 1 squared, which is 1. So to complete the square, we're adding 1, but we're going to turn right around and subtract 1. Notice if I simplify this line, I'm right back to this line here. Each line needs to be equivalent. Okay, now this is the tricky part. Only this part here is the perfect square. We do not want this negative 1 inside of the parentheses. So if we want, that came in too soon, sorry, just ignore it. If we want to get rid of this one here and move it over here, well, what is the effect of negative 1 sitting there? The 3 gets distributed to negative 1. So by putting a negative 1 there, what we're really doing is subtracting 3. So notice as I rewrite this, I have the 3, but I only have x squared minus 2x plus 1 inside of parentheses. That negative 1, that minus 1 is no longer there. I still have plus 12, but moving that negative 1 out to the side, it is now minus 3. Okay, after that it's pretty straightforward because what we have here is a perfect square. And if we're wondering, what is that number going to be? You can go ahead and factor that trinomial, but this number is always b divided by 2. So negative 2 divided by 2 is minus 1. And we have completed the square. The vertex is now standing out. That is going to be positive 1, comma, 9. The axis of symmetry, which came in a bit too soon, is x equals 1 because that's the equation of the vertical line. The y-intercept, the plus c up there, that's what gives us our y-intercept. So that's the coordinate 0, 12. And opens, well, the number a, here, 3, positive 3, since it's positive, it's smiling, and so it's going to open up. Putting all of that together, we would graph this parabola. Okay, let's look at another one. Now, in this example, it is very similar to the example we just did. So if you feel really good about the example we just did, then you can fast forward and go to the next example. First thing you want to decide is if that leading coefficient is 1. It is not 1. So what we do is take this number here and slide it over to the side and factor out the leading coefficient out of the front 2. So if I factor out 2, that's going to leave me with x squared minus 6x, and then we still have minus 1. Next, we want to think of a number that's going to make inside of parentheses a perfect square. To do that, we just take negative 6 and divide it by 2. Square it, we get negative 3 squared, which is 9. So the number 9 completes the square. But because every line has to be equivalent to the line above it, I can't just randomly put a plus 9. I have to also subtract 9 to keep it equivalent. Okay, now this x squared minus 6x plus 9 is a perfect square, and we don't want that negative 9 inside of there, so we want to move it over here. But you can't just write minus 9 over there, because the effect of placing negative 9 inside of parentheses was 2 multiplied by negative 9. The effect was minus 18. So if I remove this negative 9 to move it over here, when I move it here, that value that I put here is going to have to be negative 18. There we have it. So 2x squared minus 6x plus 9 is right there, the minus 1 right there, and then moving that negative 9 out here is really writing minus 18. Now we have a perfect square, so we can rewrite this as a perfect square. You can factor x squared minus 6x plus 9, but the shortcut is this number is always going to be b divided by 2. So negative 6 divided by 2 is negative 3. And when I simplified negative 1 and another minus 18, we have negative 19. From there, you could find the vertex and make your sketch, but I'm just going to focus on the process of completing the square. Here we have another problem. I'm going to go through this one very rapidly because it's much like the last two. But for some reason, when students see just a negative in front of x squared and they ask themselves, is the leading coefficient positive 1? They forget. Oh my gosh, it's not. So I took the negative 5, slid it over to the side. I'm now going to factor out negative 1 from the first two terms. So if I take out negative 1, I have x squared. Factoring out negative 1, I have minus 12x. Next, I want to think of a number that makes this a perfect square. So we take negative 12 divided by 2 and square it. We get 36, so we're going to put in 36, but because every line has to equal the line above it, I can't just randomly throw in 36. I'm going to have to undo that with a minus 36. I do not want this minus 36 inside of parentheses because the x squared minus 12x plus 36, that's what's creating the perfect square. So I want to get that minus 36 out of there. So the minus 36, by putting that minus 36 there, the effect, that negative 36 was negative 1 times negative 36. So the effect of that negative 36 is adding 36. So if I remove this minus 36 and put a number over here, I'm going to have to put plus 36. This is where a common mistake happens because students say, oh, I'm going to fill in this space with negative 12 divided by 2 squared, and they get the 36, and they say, oh, I'm going to undo it, so I'll write minus 36. Yes, it was minus 36 to undo it, but because that negative out front changes that to a plus 36, we have to put plus 36. All right, we have a perfect square, and negative 5 and 36 make 31. The number here is always going to be b divided by 2. Negative 12 divided by 2 is negative 6. Now we have the vertex, which would be positive 6, 31, and so on. This is the last example, and it is the trickiest. If you have been following the pattern, it's really not that challenging, but we do have a lot of fractions. So I'm going to take this one a little bit slower. The first thing we ask ourselves is the leading coefficient positive 1? It is not. So we're going to take this negative 5 and slide it over to the side to get it out of the way. But we're going to factor the number 2 out of the first two terms. Now, some of you hopefully are thinking, wait a minute, factor a 2 out of 3? You can, yes. It's not uncommon, but you can force a 2 to come out. If you want a 2 to come out, what you're doing is 2 divided by 2. Whatever number you're trying to factor out, what you really did was divide by the number you were factoring out. So 2 divided by 2 is 1, forcing that leading coefficient to be 1. And then 3 divided by 2, because 2 is what we're taking out, is 3/2. Now run that back through just to verify in your mind that this line is equivalent to this line. If I distribute the 2 back through, 2 times x squared is 2x squared, and 2 times 3/2 x is right back to 3x. So you must take whatever number is in front of the x squared out of the front two terms. And it's okay if it doesn't fit in evenly into this number. Whatever number you factor out is what you're dividing these two numbers by. Okay, now we want to think of a number that completes the square. To complete the square, we divide b by 2 and square it. I know it's a fraction, darn it. Oops, I will scoop myself over. So 3 over 2 over 2 squared. That looks kind of ugly, so I'm going to write it like that instead. When you divide by 2, that's the same thing as multiplying by 1/2. 3/2 times 1/2 is 3/4. 3/4 squared is 9/16. To complete the square, we're going to add 9 over 16. But when we add 9 over 16, this line has to equal this line. So I'm going to turn right around and subtract 9 over 16. Just like before, we do not want this minus 9 over 16 in there. We want it over here so that what's left in the parentheses is a perfect square. So I can't just take this negative 9 over 16 and throw it over there. The effect of putting negative 9 over 16 in this spot is 2 times negative 9 over 16. Okay, so I'm moving that over, and to find out the number I should write there, I'm taking 2 times negative 9 over 16, and that is negative 9 over 8 when we multiply those together. So this one is going to be gone, and now we're going to have negative 9 over 8. Okay, there we have it. Okay, we can combine negative 5 minus 9 over 8. That'll be the number here on the end. And then this right here can be factored. Again, like, what? Factor that? Look at all those fractions. But that's why we want to make these observations. Okay, when we write that, here's the negative 5 minus 9 over 8. There's that fraction. And then what's going to go here? You don't have to think very hard. It's always the b term divided by 2. When we took 3/2 and divided it by 2, we got 3/4. 3/4 is what goes there. So if I were to take x plus 3/4 multiplied by x plus 3/4 and FOIL it together, I'd be right back there. So we've completed the square. The vertex would be negative 3 over 4, comma, negative 89 over 16. We could plot that point. The vertex, that would be our vertex. The y-intercept would be negative 5. We would have the axis of symmetry would be x equals negative 3/4. And because the leading one here, A, is positive 2, we would have a parabola that is smiling. This would be an excellent problem to write down in your notes because this is probably the most challenging kind you can face. So if you want, maybe even re-watch just this one example.